Okay, it's 5:25, so let's get started. A lot of people don't come Friday.
You can tell us the secrets on Friday.
Yeah, I could tell you secrets, but we'll figure out something. All right, so a few announcements. P-Set 2 is being graded, and hopefully they'll be done by either tomorrow or Sunday. I'll let you know, as always. P-Set 3 is out, so any questions about P-Set 3? And it's highly likely it will not be pushed back, yeah.
I don't understand what my name is even talking about for the proper setup.
Which one?
For the very first problem.
For the first one? Yeah. So it's this thing called edit distance. And it's asking for all strings of the form W with a delimiter in between. Then some other reverse string where W and X are strings that only contain A, B, and C, and the edit distance between W and X is at most 1. So that's what the language is saying. So if I have two strings whose edit distance is exactly 0, what can I say those two strings are? They're identical strings. So this includes W # W reverse for all W, because that's an edit distance of 0. I made 0 modifications from W to get X. Okay? I'll say why it's reversed in a second. So I made 0 modifications to get from W to X. Well, what are the 3 possible modifications that could be made from W to get X? Well, as said in the problem statement, either an insertion, a deletion, or a substitution. Okay? So so this is for insertion, W # W, or not W, X reverse, if W equals W1, W2, up to Wn, and X is W1, W2, Wi-1, I'll put N for new character, Wi through Wn. So all I'm saying here is that wow, that was a bunch of words. To get from W to X, I had to insert a character. But it can occur anywhere in the string.
And it can occur on either side.
Yeah. No, from W to get X. This is in the case of insertion.
Oh, yeah.
Yeah. So this is insertion. There can also be deletions. Deletion. So we do the same thing, and X is W1, W2, Wi-1, Wi plus 1, Wn. So I can delete any character of W, get X. And I include that string W # X reverse. You look really lost.
It's the reverse part.
Yeah. So does anyone know why I make it reverse?
Use stack.
Yeah, I use a stack, but what if I said not reverse? Just W # X. This language would end up being not context-free. So the reason I say reverse is that you can use either a stack for a PDA really easily or a grammar really easily. So like if I have the language in general, W # W reverse, where W is in, say, 0, 1 star, can I make a grammar for this? Well, if it is really W # W reverse, well, what does the very next character on both sides of the # have to be? The same. So then I can make a grammar like, well, I got to make a single £, or 0s0, or 1s1. So this would handle the case of having edit distance of 0. But then edit distance of 1, you need to be able to say, okay, well, up to that deleted, well, let's just say in the case of insertion, up until that where that inserted character is, what do you know about those two parts? Starting from the pound sign and going out. Before that insertion took place, what has to happen before that? They have to be exactly the same. Then the insertion happens, and then after that, what has to happen? They have to be the same, but just reversed, but they have to be the same, okay? So an example string, so it's over A, B, C are the characters. So an example string that has edit distance of 0 is this one, because I've made no changes to get from the first half to the second half reversed, because the second half is just the first half reversed. But if I wanted to do an insertion, let's say, then this would be an example. Because looking at this reversed is just A, B, A, C. So in order to get from A, B, C to A, B, A, C, I had to insert an A. So I include that string as well. But I would not include the string A, B, C, C, A, B, A. Because in order to get from the first to the second, I had to do 2 insertions. Okay?
So the one on the left is accepted, the one on the right.
Yeah, so these are accepted, and this is not accepted.
Okay, and that's what we need to make our,
Yeah, you need to make a PDA for,
the ones that are
yeah.
accepted.
So first make one that, well, here's a good strategy. Make a PDA that has handles the case of exactly 0 edit distance, then handle one that has only exactly one insertion somewhere, then exactly one substitution, then exactly one deletion. Then do a union on all 4 of those. Yeah, so there are many strategies you can do with this, but one strategy is, well, all the strings are either edit distance 0 or edit distance 1 insertion, edit distance 1 substitution, or edit distance 1 deletion. Just make a PDA for each one of those 4 cases, and then union all of them together. Because we have easy closure under union. Yeah.
So I'm looking at the problem and it says that like it's produced a PDA that recognizes edit 1,
Mm-hmm.
and like it says, okay, so like for edit K, the edit distance is less than K.
Less than or equal to.
What?
Less than or equal to.
Just strictly less than.
It says less than or equal to in the language.
It says less than K. I'm looking at it. Am I crazy? Less than.
Zoom in on the page.
Like where the edit distance is less than.
Zoom in. Sometimes the horizontal line of less than or equal to is not shown.
Oh wait.
Yeah, zoom in.
Okay, no, sorry. On the actual thing, it's less than equal to K, but then like in English it says the edit distance is less than K. So
I'll fix that.
okay, like I swear I'm looking at it, I'm not crazy. Okay, so you want it to be less than or equal to.
Yeah, the formal description of the language is correct. Yeah. Well, if it was less than 1, then that'd be really easy.
Yeah, that's what I thought. So I'm like,
Yeah.
there must be.
Yeah.
Okay.
Yeah, less than or equal to K. Yeah, thanks for the correction.
So, right before you talked about, okay, make one that handles nothing, just the same,
Mhm.
and then substitution, interpolation, union. That's one that handles everything. Isn't that not in edit 1? That would just be accepting edit 0. So would edit 0 or edit 1 also take edit 0? Is that okay?
Well, it depends on how you. Yeah. So it would include it because edit is less than equal to 1. So it would include the 0 case. Yes. Mhm. Other questions about P set 3. Okay, so one other announcement you may want to pay attention to. So midterm 2 is on Wednesday. So I'm just going to talk about it today. I said I'd talk about it Monday, but might as well talk about it today. So 75 minutes, just like last time. No changes there. 6 problems. So this is the same as before. Same as before. Okay, and it's out of 180 points, so 30 points each. Full credit is 150. So in effect, there are 30 bonus points. Okay, and it'll cover everything that whatever we talk about through Monday. Just like last time.
So from the beginning of
Yeah.
class to
Well, yeah. So a lot of people will probably ask, like, what's going to be on it? Well, the class just builds upon what we've done before, but I'm not going to specifically ask things like convert NFA to DFA or whatever. But knowing that NFAs and DFAs are equivalent, that may or may not be important. But like things covered after midterm 1 are certainly going to be more heavily weighted for sure. Okay. Any questions about midterm 2? I'm surprised. I thought there'd be more.
at the second hour as well.
Yeah, second hour is, well, second hour 15. But yeah. Sure. All 6 problems will be long answer. There will be no true false this time. Well, the average on all the other questions was about the same as the true false, so it didn't really matter. And don't expect this exam to be easier. Okay? But there's no true false this time. I can promise that. Other questions?
Oh, we had talked about the ability to have more scratch paper.
Yeah, so what I have done is it'll come, instead of 4 sheets now, it'll come in 5 sheets. And the questions will be on, so it's front and back just like before. And the first 7 front and backs will be questions, and the last 3 will be rough work pages that won't be graded. But I provided a whole extra sheet for rough work if you want it.
Still just the one sheet for.
Yes. Mm-hmm. Yep, exactly the same. Other questions? Okay. So what did we talk about last time? Yeah, Turing machines, and what were we able to see throughout the end of last time? Yeah, right. So we talked about multi-tape machines, and we were able to prove that we can convert any multi-tape Turing machine into a single-tape Turing machine that has the exact same language. Okay?
And the only difference was the efficiency, right?
Yeah, so there is an efficiency difference, but we're not going to care about that here. We just care, does it have the same language or not? Okay? And we were able to come up with some other variants of machines, like if we wanted to reset to the beginning of the tape, or if we wanted to stay exactly where we are, or come up with a number of things, we could show that is equivalent to the standard single tape deterministic model. All right, so there's one more I want to talk about, and those are called non-deterministic. Everybody groans. Non-deterministic Turing machines. Yeah. This one will hopefully be not that bad. So the idea here is that instead of going to a single triplet, which means the state that I'm going to, symbol that I'm going to write, and whether I'm going left or right, I can go to any number of possibilities. So just as a generalization of what PDAs were able to do, let's make a generalization here. So the transition function here will be, oh, not sigma here, it's gamma. So the left side is the same. I have a state that I'm in and a symbol that I just read off of the tape. But I can go to any number of state, symbol to right, and left, right combinations. So the standard model just didn't have a power set here. Here we're just saying you can go to any number of those possibilities. So at any point there may not be a transition to apply or many transitions to apply. So right off the bat, it's immediately clear that non-deterministic machines can do at least as much as deterministic ones because it's pretty easy to convert a deterministic Turing machine into this one just by making all of these sets of size 1. So just convert whatever it would have went to a set of size 1, just like how we converted DFA to NFA. But here, now we want to consider, is this model even more powerful than the standard deterministic model? So in order to do that, we need to first talk about what does it actually mean to accept in this model, okay? So we accept a string W if and only if there is some sequence of non-deterministic choices that get to Q accept. So as long as there's some computation that leads me to accept, I'm going to say accept to that string. Just very analogous to what NFAs did and to what PDAs did. As long as there's some computation that accepts, then this non-deterministic Turing machine is going to accept. Okay? So non-determinism works exactly the same here as it did previously. But now we got to figure out, we had these two different types of languages or two different types of Turing machines that we could have, a decider or a recognizer. So for a decider, so so say that a non-deterministic Turing machine, which I'm going to just abbreviate as NTM, is a decider if it's a decider, it won't, but consider the cases of where it makes bad choices, right? It just makes bad non-deterministic choices. Well, if it's a decider, we want it to always halt no matter what it does. So we're going to say a non-deterministic Turing machine is a decider if all computation paths halt. So no matter what non-deterministic choices are made, it will always halt and say the correct answer, but it'll always halt. Okay? Any questions about that? Yeah.
What do you mean when you say like something halts?
The machine ends in Q accept or Q reject. Yep.
We don't always articulate the Q reject because we don't unwritten transitions.
Well, there is a Q reject, but we're not necessarily worried about that here. Yeah. And when we're going to be converting a non-deterministic machine into a deterministic one, we'll only worry about accepting because all other paths will reject anyway.
So just to make sure before we move on, the
decider, it doesn't mean that it all has to be accepted. It just means it has to go to one or the other.
Every path stops at some point.
Okay, so
Yeah.
but it doesn't always have to be in Q accept.
No. If it ends in Q reject, that's a halting
Okay.
computation. Yep. Other questions? Okay. So what we want to do is convert a non-deterministic Turing machine into a deterministic one. So what was the name of the strategy that we used several times last time to convert from this other model into the standard model? Simulation, right? We had the standard Turing machine simulate what the other model would have done. So here, what we want to do is, or what seems like a good idea is, simulate the non-deterministic choices that are made, and then just simulate what the non-deterministic Turing machine would have done. But how do I know what non-deterministic choices were made? I don't. Is there another strategy I can try? It's not power set.
Turing machines?
Not multiple Turing machines, multiple of something. Not TFA. We will use multiple tape, but the strategy, I mean. Well, let's say that I'm in the very start configuration right here, and I may have some number of choices that I could make. I don't know how many at first, but let's just say that I have 3 choices. And let's say that the first one, there's no choices at that point. The second one, let's say, has 4. And the last one, I don't know, let's say 2. So what I'm building here is what's called a computation tree. So it's just building what computations could have been made. It's actually also called a configuration tree. The name's not really important, but the idea is that we're looking at all the non-deterministic choices that could have been made. So at the first level here, those are the 3 possible configurations or computations at that particular moment for the non-deterministic machine. And the second level tells all of the possible configurations after we apply 2 transitions. Okay? And let's suppose that if we keep looking and we come down here, there's some configuration way down here that is an accepting one. So let's say that that's an accepting configuration. Well, the non-deterministic machine, if there is such an accepting configuration in this tree, is going to be able to find it at some point because it'll just make the correct non-deterministic choice to eventually get down to that configuration that's accepting. But I have a deterministic machine, and I'm trying to simulate this non-deterministic machine. Is there any strategy that I might try? Well, since I'm trying to simulate the non-deterministic machine, I know what transitions there are. So could I just try all of them? So here's a strategy that's bad, and I want you to tell me why that's bad. So I'm going to explore this tree so let's say I'm going to use a different color. So I'm going to explore that edge first, and then I'm going to keep going this way, and then keep going, and then keep going, and then hopefully find it. Yeah, what's the size of this tree?
Like 2 to the 10.
Wait, does a Turing machine always have a transition to apply in a standard deterministic one? Does it always have a transition to apply? Yeah. So what's the size of this tree? is infinite, potentially, because of and non-deterministic Turing machines could even have more, could make the tree even larger, even faster. So this tree could be infinite. So if I explore it depth first, could I run into trouble? Yeah, because I may keep going left, 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 and I'll never find it. Is there another strategy? Breadth first. That's a good idea. So let's say that I have the same thing as before. So if I look at all of the computations of length 1, then if I don't find it, then what? Then I'll try all, but I should start back up and I'll try all computations of length 2. Then, if none of them are accepting, go back, try all computations of length 3. Okay? Does this work? Well, if there is an accepting configuration somewhere in the tree, will I find it? Yes, I will find it eventually. But consider the possibility that there are no accepting configurations in the tree at all. So in other words, it rejects the string. What would I do if I keep trying this strategy? Could I run forever if the non-deterministic machine was a decider before? No. And why is that?
Because it has to have an acceptance state.
Right. Well, they do have them, but the idea was close.
There is a computation that ends.
I'm not sure what that means.
Well, if it was a decider, then
Yeah, so if it's a decider, then every computation must stop at some point. So therefore, if I did this where the non-deterministic machine was a decider before, I'll explore every computation path, and therefore every path must halt. Because every path halted before. It may take a lot longer to explore this tree, but it must halt. So consider the case where the non-deterministic machine was a recognizer. So I only needed to halt on the strings in the language. So there are two cases. If there was an accepting configuration in the recognizer's tree, will I still find it? Yes, because it's in the tree, I'm exploring it breadth first, I will find it. But now consider the case of where it's not in the tree. There's no accepting configuration in the tree. What would I do?
Just go on forever.
I would go on forever. Is that a problem?
Yeah. I mean, no.
No. Why is that not a problem?
Because it can go on forever theoretically.
Did the non-deterministic machine accept or reject that string? Or did not accept that string? There was no accept, it was only a recognizer. There's no QAccept in that tree anywhere. So did it accept that string? No. Does it have to halt on the strings not in the language? No. So am I required to halt if it's not in the tree? No. So I only need to halt on the strings in the language, and I guarantee I do. So let's recap. So if the non-deterministic machine was a decider, then 1, if accepting config in the tree, then the deterministic machine will find it. Or 2, if otherwise, then all computations halt by definition of NTM Decider. Okay? Oh, yeah, sorry, my horrible handwriting. The deterministic machine. Yeah. The deterministic machine will find it because it's exploring the tree breadth first. But I don't know whether or not that, well, you say, well, every computation branch must halt in a decider, so why don't you do it depth first here? But I don't know whether or not a Turing machine given to me is a decider or recognizer. I'm just supposing if it was a decider, then it either finds it by doing breadth first, or if there's no accepting config in the tree, then it'll just explore the whole tree and all paths halt anyway. So therefore, my deterministic machine will also halt.
So that just means the tree's not infinite, right?
Yes, but I don't know. It's not given to me.
Yeah,
Well,
so we don't know. It's just
yeah, it just if it happened to be, then you can explore it any way you want, but you don't know that up front. But if the NTM was a recognizer, then one, if accepting config and tree, the deterministic machine will still find it again. Or two, if otherwise, as this class goes on, my handwriting gets worse. If otherwise, then we run forever. But okay, because the string was not accepted. Jeez, can't write. Accepted by the NTM. And so therefore, I will get exactly the same language. Why? Because in the decider case, I will accept the string if the NTM accepted it. But if the NTM rejected or did not accept the string, then I'm just going to explore all paths and never accept anyway. If it was a recognizer, if the NTM accepted it, I will find the string just as before. Or if it doesn't, then I will run forever. But that's okay because I don't have to halt in a finite amount of time. So if the NTM was a decider, the DTM is a decider. If the NTM was a recognizer, my deterministic machine is also a recognizer. Okay? So this strategy of trying all possible paths works in some cases like this, where you just try every path breadth first, and if you find it, then accept. If not, keep going into the next level. Okay, any questions about the idea? So, yeah, go ahead.
The notation between the difference between a decider and a recognizer is purely on the...
Yeah, so let's just recap. A recognizer is just a machine that always halts on the strings in the language.
Right.
A decider is a Turing machine that halts on every string, not just the ones in the language, but also the ones not in the language as well. It halts and rejects those because they're not in the language. Okay? So it's just a machine that always stops.
And in the case with the balancing, right, for the recognizer is an acceptable...
We're not worried about that. It's just a minor detail. It'll turn out that we can actually take a high-level approach to this, something called the Church-Turing thesis. But other questions? So the question about multiple tapes. So how would I actually perform this on the deterministic machine? Well, what I want to keep around is the input string, because our strategy was try all the computations of length 0, then try all the ones of length 1, then try all of them of length 2. So I got to remember what the starting configuration is. And by doing that, I need to remember what the original string was. So on one tape, I'm going to keep the input. And I'm never going to modify this. Not unmodify, no modify. Okay? So now what do I need to keep track of here if I'm trying this breadth first strategy? So what do you need? So remember back to breadth first search. What do you need to keep around in order to look further into the graph? Well, level, but what things am I keeping? The quote unquote leaves, what is called the frontier of the graph. So if I've explored one edge, all possible one edges from my starting vertex, I need to remember all those vertices. So is there a nice way that I can remember that here? Well, I don't necessarily need a stack here. I can just use an extra tape. So what I'm going to do is I'm going to keep an extra tape separated by a delimiter. So this is, so I'm going to keep track of the various configurations. Are each of the vertices in this tree. Yeah.
It's where the
Yeah.
thing is pointing, right?
Yeah, so it keeps track of what the current cell contents are, where the tape head is, as well as what state we were in.
Okay. Also a question. Can you go over a refresher of how that was set up again?
How what was set up?
The configuration. It was like where the tape head is, and
Yeah.
their state, and then the rest of the input stream.
Yeah, so these guys contain, let's see, contents, tape contents, I should say. Tape head position and which state of the non-deterministic Turing machine. It's not necessarily important here, but the
Okay, so it doesn't matter. We just need to know.
Yeah,
that that's
yeah,
that information.
yeah, I covered that last time, but the idea is if tape contents are W1 up to WN, tape head position is I, so I'm looking at WI, and state is Q, then the configuration is W1, W2, up to WI minus 1, Q, WI, WN. So it's just a compact way of saying the contents are all the W parts, the state is Q, and the thing directly to the right of the state name is the thing I'm looking at. Okay? All right. So yeah, go ahead. I didn't hear.
Are you able to remove things from the tape?
What do you mean remove from the tape?
Like in a stack, you'd be able to pop.
Yeah.
Tapes always,
Mhm.
you can only leave from them.
Well, remove in the sense of push everything to the right of me, left one position.
It's still on the tape.
Yeah, still on the tape. There's no like remove cell operation. That'd be a good exam question, but I won't ask that. But
Not like a stack in that sense.
yeah, it's not a stack, but you can operate it like a stack. Yes. Yeah, but I don't need it to be a stack here. And so if I explore one level further here, what do I just need to do? I just remove, I don't need, yeah. So I'm gonna make another delimiter, like a double delimiter here, and then put all of the things, all of the configurations I reach after another step to the right of that, that double pound sign. And then, once I've explored all possibilities, I remove everything to the left of that double pound sign. And then try again. Yeah, move, yeah. So I shift left everything past the double pound sign all the way to the left of the tape. Or I can keep it around. It's not that
So
important.
it's kind of like a stack then. in that,
Yeah, it's-
or a queue in that.
It's like a queue, yeah. Because that's actually how BFS operates, yeah.
And you can do that because you've already converted everything.
Yeah, I could keep them around, but I like keeping my tapes clean, but it's not that important of whether I keep them around. It actually may be nice to keep them around because then I don't need to erase the tape every single time, but there's no need. There's no difference.
Can you go over again, what do you do with the double pound?
Yeah, so that's just telling me what my frontier is, and then after the double pound sign, what things I can reach after another non-deterministic transition. Okay? So it's like the things that I've reached so far, and then after is the things I can reach after one more transition.
Okay, and we don't care what's before it.
No, yeah, so that's why I said you could shift everything left, but it's not that important here. Other questions?
In your example of C1, half C2,
Mhm.
half C3, those are indicative. Can we bring back your diagram?
Yeah, sure.
for it so we can-
Yeah, so I'll bring this down. Yeah,
we can map the diagram to what you have.
yeah, so, yeah, great point. That might be helpful. So, make it smaller. All right, so then I actually had 3. So this could at one point represent C1, this is C2, and this is C3. Then after and let's just call these guys C4, C5, C6, C7, C8, C9. Then after the double pound sign would be in no particular order, C4, C5 through C9. Yeah. Okay. Yeah, so the key point here is that we're just brute force simulation of all the non-deterministic choices that can be made. Okay? Yeah. Yeah, so I do not care about efficiency here at all. This will take a monstrous amount of time comparatively, but I don't care. As long as it has the exact same language of the non-deterministic machine, everything works. Okay? And I run in a finite amount of time. That's the another important bit. Yeah. Yeah, so I should write it here. I didn't have it before. It's like C4, C5, and then all the way through. Yeah, so it's just an implementation detail. So we'll be talking about low-level descriptions versus high-level descriptions in a bit. And what this is getting to a low-level description in terms of what I'm doing to the tape. So like I'm telling you, you put this double pound sign as a separate delimiter, but like any reasonable person implementing this will put a delimiter there. So I can just say, put C4 through C9 on the tape after C1 through C3. Then you know that there should be some delimiter there. Okay? Other questions? Was it the XKCD post that was like non-deterministic machine? So I don't have it with me, but there's this great comic about like some student in a class like this, and the teacher was talking about, so we convert a non-deterministic Turing machine into a deterministic Turing machine, and there's a thought bubble around the student, and the student's thinking, Man, I just wanted to design video games. I thought that was a great comment, and we finally reached that point, so I thought it was appropriate. But any questions about the how we were able to brute force convert a non-deterministic machine into a deterministic one? Okay. Unless there's, okay. So thank goodness there are no more of those type of things that we'll do about converting between different models. But I want to talk about a different type of computation. So the idea of DFAs, NFAs, PDAs, and Turing machines now was that we put the string onto the tape or wherever, and we run the machine, and it says either yes or no, or in the case of Turing machines, could run forever, and therefore doesn't accept. But maybe what we can do is, instead of trying to recognize strings and say yes or no on them, what we can do is instead output the strings in the language. Okay? So instead of taking strings in and saying yes or no, we're going to output the strings in the language. So, for example, if I wanted to output the integers, let's say, then a sensible way I can do it is 0, 1, 2, positive integers, 3, 4, 5, that. And so think about this strategy of how I'm enumerating these. So will I print every integer in a finite amount of time? No, because there are infinitely many. Now consider another question. Fix your favorite positive integer. Will I print it in a finite amount of time?
Yes.
Yes. So that's an idea that we may want to try. But consider a really dumb way of printing out the integers, which is this. 0, 1, 2, 2, 3, 3, 3, 4, 4, 4, 4, 5, 5, 5, 5, 5. So the numerical value of the number, I print that many times. I'll ask the same question. If you fix your favorite integer, will I still print it in a finite amount of time? Yeah. So that's the idea of what is called an enumeration of the integers. So the correspondence with Turing machines is called an enumerator. So instead of talking about integers, we're going to talk about the strings in a particular language. And we'll say that a Turing machine is an enumerator if it prints fixed a string, that string, within a finite amount of time. So yeah, go ahead.
So this is in a sequence. It doesn't have to be sequentially.
No, it does not have to be sequential. So I could do 5, 4, 3, 2, 1, 0, 10, 9, 8, 7, 6, like every 5 reversed. That's an enumeration of the integers. And I could have repetitions. As long as I can guarantee that fixing an integer and I will print that particular integer in a finite amount of time, then it's an enumeration. So I'm enumerating the integers in some way. The first way is what is called standard lexicographic order. But I can print them out in any way, as long as I can guarantee that if you have your favorite integer, it'll be printed within a finite amount of time.
You guarantee that how? Because you have infinitely many zeros.
So if I, like in this strategy, if I add 1 to every integer, I will hit your favorite integer in a finite amount of time, guaranteed. The second one, well, it'll take a lot longer to get there, but it'll get there. In the third one, if I do this strategy of 5 and then shift up 5 backwards, shift up 5 backwards, I still will hit it in a finite amount of time. Okay? So an enumerator is a Turing machine. So we're back to single tape deterministic here. Okay? Enumerates, so this is another term, a language L if the Turing machine starts with empty tape, and by empty I mean all blank. If it starts with empty tape and writes, so pound sign here is a delimiter. Pound sign W1, pound sign W2, pound sign W3, pound sign W4, pound sign, etc. Where each WI is in the language and in a finite amount of time. Fixing a WI, it will be printed. Okay, so I'm not saying, so what it's doing is it will print a string in the language L in a finite amount of time, delimiter, then print maybe a different string in the language, maybe the same one, delimiter, keep going, keep going, keep going. And you can actually see that an enumerator never stops. It'll never stop, certainly if the language is infinite. But if it's finite, we'll say that you can always ask for the enumerator to put out another string. So an enumerator, like for the first time I say, print out some string in your language, it prints out a string. Then we can ask it again, print another string, print another string, print another string. And we can do that as many times as we want. Okay? Yeah.
Does the enumerator have to be in
No, so it's enumerating a language.
Oh, okay.
Yeah, so for pick your favorite now string in the language, it will be printed within a finite amount of time. Okay? Good question?
Kind of like, well, I'm gonna get you in my head, but I have a question.
Yeah.
It's kind of like power set for languages.
No, because it's just printing out the strings in the language. It's not doing the,
All the possible combinations.
no, it's printing a single string at a time and then another string, then another string in the
Yeah, but
language.
it's all of the possible combinations of the language.
I'm not sure what combinations of the language means.
Like all of the possible ways, all of the possible strings in a language is printing them all out, or is it just?
Yeah, so we're not concerned with how the enumerator is going to actually print them out. All we're guaranteed is that it'll print each string in a finite amount of time. Like fix a string, it'll print it out. Yeah.
And so there's no constraints about W1 versus
No, like the first 10 trillion could all be the same. Yeah, but that'd be a dumb way to do it, but as long as it's in a finite amount of time. Okay? So we say that L is enumerable if some enumerator enumerates it. Yep. Mm-hmm. Yep, I do mean that.
Why do you get all the easy proofs?
Yeah. So as long as there's some enumerator for the language, then we call it enumerable. So,
That is not cyclical.
what's sorry?
That is not defining something with definition.
No, it's defined based on enumerator.
Where? So the enumerator is something that enumerates. That's what you're saying.
Yeah, so we say a Turing machine enumerates a language if it operates this way, and we call it an enumerator. Okay? So, yeah, so I kind of did a double definition the first time. Okay? Any questions about that, though? So you may be concerned that now we're talking about decidable, recognizable, and enumerable languages now. It's like, holy smokes, it's getting out of hand now. But it actually turns out that we can show this, that recognizable and enumerable languages are the same. So if I can recognize a language, it is enumerable. And if I can enumerate a language, then it's recognizable. Okay? So by that definition, every decidable language is enumerable. And we haven't shown anything else other than that. Okay? So if I want to show that two classes of languages are the same, how do I do that? Yep, so I convert one to the other, and then the other way. Okay, so the easier direction we're going to do first after the break.